Intensity of an atomic beam produced by a vapor. An atomic beam of sodium atoms is produced by maintaining liquid sodium in an enclosure at some elevated temperature T. Atoms of sodium from the vapor above the liquid escape by effusion through a narrow slit in the enclosure and thus give rise to an atomic beam of intensity I. The intensity I is defined as the number of atoms in the beam which cross unit area per unit time. The latent heat of vaporization per mole of liquid sodium into a vapor of sodium atoms is L. To estimate how sensitive the beam intensity is to fluctuations in the temperature of the enclosure, calculate the relative intensity 1 over I di dt in terms of L and absolute temperature T. So first of all, I realize that we're talking about flux here. So what I'm calling intensity is the flux of particles, which we have found out in chapter 6 to be approximately 1 over 4 number of molecules per volume multiplied by their average speed. And we have the ideal gas law, P bar V is equal to capital NKT, ideal gas law. And at the same time, we can write this as P bar is equal to NKT because N is capital N divided by V, number density. So N is P bar divided by KT. So for N, I can substitute P bar divided by KT. For V bar, I can use the following Equipartition Theorem. So 1 over 2 mv square bar is equal to 3 over 2 kT for these molecules that are free to move. So I can write v square bar approximately equal to v bar square. So I can say that v bar can be approximated as square root 3 kT over m, which actually is the RMS value, but the mean value is close to the RMS value, if you remember from the Maxwell speed distribution. Therefore, I find that v bar varies as square root kT divided by m. So that's the temperature dependence of v bar. So if I look at the flux of particles, which is a number per area per unit time, so this is the intensity. The intensity is proportional to n times v bar, where n is proportional to p bar divided by kT, or n bar is n is given by p bar divided by kT. V bar is proportional to square root kT divided by m. So if I look at the natural logarithm of I, this is going to be a natural logarithm of some constant, proportionality constant C, minus 1/2 natural logarithm of KT. So here I can actually get rid of, so I can also write this as, let's see here, P bar m to the power minus 1/2, and it is proportional to KT to the power minus 1/2. So square, I can take KT square into the square root, so I get 1 over square root KT. So it's KT to the power minus 1/2. So I can absorb the dependence on pressure and mass as the proportionality constant into the proportionality constant C, and then I have this 1 over 2 natural logarithm 1 over 2 natural logarithm KT. So what I'm trying to calculate here is the derivative of natural logarithm of I with respect to temperature. This will be equal to minus 1 over 2 kT multiplied with K, but P bar also depends on temperature, so here I have made a mistake. So I should include, while m is a constant, there is also the natural logarithm of P bar here, which is temperature dependent. P bar is temperature dependent. So I have plus the derivative of natural logarithm of P bar with respect to temperature. So the k's will cancel here. So I'm going to get minus 1 over 2t. Then I will have the derivative of natural logarithm of P bar with respect to temperature. For that, I remember the Clausius-Clapeyron equation. So let me stop here and recall the Clausius-Clapeyron equation. dP bar dt is delta S over delta V. It's the latent heat of vaporization divided by the temperature T times delta V, and delta V is approximately equal to the volume of the vapor. So this is basically going to give me P bar is V is equal to nkt. So for the volume I write nkt divided by P bar. Or if I define this volume per mole, so this would be equal to number of moles nu RT divided by P bar, but if nu is equal to 1, then it is volume per mole, because L is the latent heat of vaporization per mole as well, so it was defined per mole. So therefore this is going to become dP bar dt is equal to the entropy change Q over T delta V, which is equal to latent heat per mole divided by T RT over P bar. So I find that dP bar dt is P bar L over RT square. So 1 over P bar dP bar dt is L over RT square. So d ln P dt is L over RT square. So going back to my d ln I dt, where I had the first derivative of minus 1 over 2 ln kt giving me a minus 1 over 2t. Then I have the derivative of the pressure ln p with respect to t, which is L over RT squared. So I can take this into T2 minus 1 parentheses. Then I will have L over RT. Then I will have minus 1 over 2. So this will be d ln I dt, which is equal to 1 over I di dt. Okay, so we're doing an experiment looking at the intensity of an atomic beam produced by a vapor of sodium. So the vapor of the sodium is obtained by a phase transition from liquid sodium to gas sodium, and where the latent heat of vaporization per mole is L. We're looking at the intensity, which is the flux of particles, number of particles crossing a unit area per unit time, which we know to be 1 over 4 nV bar, where n is the number density, is related to the pressure as P bar divided by kT, pressure and temperature. And the mean speed of these molecules is varying as square root kT over m, which you can remember from Equipartition Theorem. This gives us a quick estimate of temperature dependence of V bar, or if you go back to the Maxwell velocity distribution, you will remember that the V bar value is actually somewhat smaller than square root 3 kT over m, which is the RMS value. Anyway, so it still has the square root of kT over m dependence. So the intensity is proportional to P bar over kT, square root kT over m. Square root of m is also a constant here. So I find that natural logarithm of the intensity is natural logarithm of c minus 1 over 2 natural logarithm of kT plus natural logarithm of P bar, which does depend on temperature that's given by the phase equilibrium curve. So d ln I dt gives me minus 1 over 2 kT times k, and then I need the derivative of natural logarithm of P bar with respect to temperature, which is given by the Clausius-Clapeyron equation here. Clausius-Clapeyron equation in the phase equilibrium curve. The change in entropy divided by change in volume is dP bar dt, and that is Q over T delta V, and Q is latent heat of vaporization per mole divided by T, then the volume is volume change per mole, which is RT over P bar for 1 mole. So then I will have dP bar dt is P bar L over RT square, or dLmp dt is L over RT square. So I substitute that for dLmp bar dt, and I had already minus 1 over 2t. The sum gives me t to minus 1 in parentheses L over RT minus